The comparison test is another way that you can show that a series converges or diverges. And actually, some people tried to use this on the homework that was due on Wednesday. You weren't supposed to. You were supposed to be using the integral test in that section, although it didn't specifically say. So it is, I suppose, it was legal to use the comparison test. But a lot of people did it wrong, unfortunately. Anyway, the comparison test is a way to show that a series converges or diverges. And I will just refresh your memory of how it works. First of all terms must be positive. If they're not all positive, then you just don't do the comparison test at all. It does not apply. So all terms must be positive, first of all. If they're not all positive, then you got to do it differently. But here's how it works. You compare your series to a different one. Compare your terms to some other ones, some other series. And you always write sort of, there's a bigger, which is greater than or equal to the smaller, right? When I wrote this formally last time, I'm just writing sort of a more informal version. When I wrote this formally last time, I said it was, you know, I called them ANs and BNs, and you write one of them is bigger than the other, or one is less than the other, or whatever. You compare your terms to some other series. So maybe your series is the bigger one, maybe your series is the smaller one, but you make a comparison between two of them. And then the comparison test, it says, then if the sum of the smaller diverges, then the sum of the bigger diverges. All right. The idea is if the smaller one is becoming infinite, then automatically the bigger one also is becoming infinite. And the other way around, it would say if the bigger one converges, that is, it's not becoming infinite, then the smaller one also converges. So, and if the sum of the biggers converges, that means it is not becoming infinite, then automatically the smaller one also converges. It's not becoming infinite. The sum of the smaller also converges. All right. This is the convergence, the comparison test. All right. And the hard part about it is you just have to imagine what the other series you're going to compare it to is, and you have to kind of get a feel for how you can just sort of invent your other series that you're going to do your comparison with. All right, let's just do two quick examples, and then we'll talk something new about this. Here's one that was on the homework. Now, on the homework, you are supposed to use the integral test, and it ends up being an integral involving the arctangent of something, the inverse tangent. Most people did this properly. But actually, you could have done the comparison test for this one instead of the integral test. When I look at this, it looks like basically 1 over n squared. That, like, there's this plus 4 down there, but my feeling is the plus 4 really shouldn't matter much, right? So my what I'm gonna do is basically this. I say sort of to myself in my head, this looks like 1 over n squared, right? The plus 4 I feel like shouldn't really matter in terms of is this gonna like be infinite or not. The plus 4 probably doesn't make a big difference. It looks like 1 over n squared, so I'm gonna make my comparison with 1 over n squared, and I have to decide which is the bigger and which is the smaller. You got two choices, and when they're fractions, you want to look at like the numerators and the denominators. So the fraction on the left has a bigger denominator, which means it is smaller. So the inequality should go this way, less than or equal. Actually, it is straight up less than. They're not equal, but in the comparison test, it would be okay if they were equal sometimes. All right. The one on the left is lesser because its denominator is bigger. So the one on the left is the smaller one. The one on the right is the bigger one. All right. And we know the sum of 1 over n squared converges. That's because this is a p series with the p being greater than 1, right? This you just have to remember. And so that means in our inequality, the bigger converges. Actually, it's the sum of the bigger converges. And so the sum of the smaller one also converges. All right, and this is a typical, simple application of the comparison tests. Anybody got any thoughts about this? I think some of you actually wrote this on the homework for this problem, which is correct. You weren't really supposed to do it this way, but they never said don't use the comparison test. According to Air Bud rules, this was a legal answer to that question because they never said not to do it that way. All right. On the test, by the way, you are likely to see some problems like this. I show you a series, and I just ask you, does it converge or not? If I don't say so, you can use whatever methods you want, and we have several. We have the integral test, the comparison test, or you can sometimes like resimplify the thing so that it is equal to a p-series or something like that. All right, great. Let's just try one more simple example. I just wanted to do one example of doing it wrong. So how about this one? Now, in this case, it would be natural to try the same thing. I basically look at that and I say the 3 doesn't really matter here. It just looks like 1 over n. So I would say this looks like 1 over n. And so I'm going to make this comparison. 1 over n plus 3. And just like before, the 1 over n plus 3 is smaller because its denominator is bigger, right? So 1 over n plus 3 less than or equal to 1 over n. All right, and the 1 over n, the sum of the 1 over n, this one actually diverges. This is called the harmonic series, but it's a p-series with p equal 1. This diverges. This is the p-series, p equal 1. Remember, the p-series means this, 1 over n to the power p, and it converges when p is greater than 1, and it diverges when p is less than or equal to 1. This you just have to remember. All right? The sum of the 1 over n diverges. All right? So, in this case, the sum of the bigger one diverges. That is, the bigger one is becoming infinite. This means nothing about the smaller one, though. We cannot conclude that the smaller one also diverges, because here all you said was the bigger one goes to infinity. That doesn't mean that the smaller one goes to infinity, right? That's the other way around. If you're doing a comparison test, you need the smaller one to go to infinity. That means also the bigger one must go to infinity. But this way around is not telling us anything. The sum of the bigger diverges, so we can't conclude anything about the smaller. Right? It has to be going the right way around these inequalities. If the bigger one diverges, it does not mean that the smaller one diverges. Now, it is a fact in this example, the smaller one actually also does diverge, but you can't do it this way. So in this one, you can do it using the integral test, but the comparison that I did at least will not work. So I'll just say, do it some other way. The integral test will work in this case, but the comparison test did not work. Now you might think, well, it didn't work, maybe I just made a bad choice. Maybe I should not have compared it with 1 over n. Although in this example, there isn't really a better choice that you would have made. It's just, in this case, the comparison test is not the way to go. All right, anybody got any questions? So some people on the homework who tried to use the comparison test, they did it wrong in this way. So I just wanted to show one example. All right, great. What I want to talk about for the rest of today is a fancier version of the comparison test. Fancier comparison test. This one is fancier in that it's a little more complicated, but provided that you understand how to do it, it actually is easier to do using this fancier way. It's slightly more complicated, but you actually don't have to worry so much about which direction the inequality is going, and that's what makes the comparison test can be a little tricky, because you have to make sure that you have that inequality sign going in the right direction. This fancier version does not require the inequality sign to be going in a specific direction, which makes it easier to do, although a little more complicated than mechanics of doing it. Here it's called, so I'm just going to write it as a theorem here. It's called, the book calls it the limit comparison test. The limit comparison test. And it's still about, I give you a series and you come up with another one which looks kind of like the original one, and you compare them. But you don't have to write inequalities, which makes it a little easier in my opinion. So here's what it is. First of all, you still need the terms to be positive all the time. So if an and bn are always positive, none of this comparison business works if you have a mixture of signs. So if an and bn are always positive, and here's the different, this is why it's called the limit comparison test, because it involves looking at a limit of the two things rather than saying one is less than the other. There's no inequality, it's just this. If the limit of an divided by bn actually equals something where c is not 0, this is important, and I'll just say parenthetically, c is not allowed to be infinity. C is a particular number, a specific number, which is not 0. It's not infinity. Infinity is not a number anyway, but just to make it clear. So we are still kind of comparing the a's with the b's, only in this way we are making a fraction out of them. And if it turns out that the limit of that fraction is just some particular value, not 0, not infinite, then that means how you should feel about this is it means that the ANs and the BNs are not really all that different. Like for instance, if the C is 2, it means that basically the ANs are twice as big as the BNs, right? In the limit as the n gets bigger. If this fraction ends up equaling 2, it means the ANs are 2 times the BNs. And so they're not all that different in terms of whether they converge or not. All right, the conclusion of the test is, so if this limit actually is a specific number, then the convergence of the sum an and the sum bn are the same. What I mean by that is either they both converge or they both diverge, i.e. they both converge or both diverge. And the reason why you should believe this, like I said, if this C, it turns out to be something like 2, it means that basically in the long run the A's are twice as big as the B's. And so if the B's converge, the A's will also converge to just twice as much. And if the B's become infinite, then the A's also must become infinite. So if the A's and the B's, they have the same convergence. They either converge together or they diverge together. This is called the limit comparison test. So it is slightly more like complicated. You have to do this limit, but you don't have to think about any inequalities, which in my opinion is at least like conceptually easier to grapple with, because to me inequalities are confusing. I don't know if you feel the same way, but you don't have to think about inequalities to do it this way. And in fact, all of the examples, if you could do it with inequalities, this way will also suffice. So this is slightly more complicated, but it always works, and you never have to do it with the inequalities if you don't want to. You can always do it this way instead. And so, you know, to me, unless it's like a very obvious case, I'm usually going to try to do it this way, just because I don't like thinking about the inequalities. All right, let's just try some examples. Whoa, sorry about that. All right. There we go. Okay, some examples. How about, well, actually, you can do that one that I just gave up on just a few moments ago. You can do that with this new fancier version of the limit comparison test. Something like, was it that I said? I think it was that. The sum 1 over n plus 3. Let's do this using the new fancier version of the comparison test, which is the limit comparison test. Again, you want to look at this and you say to yourself, well, this basically looks the same as 1 over n. So this looks like 1 over n, all right? And these I'm going to compare those two things. So I'll call this one the an maybe, and this one the bn. Now, actually, it ends up not mattering if you decided to do the other way around, call the one the b and the one the a. It doesn't matter. You don't have to choose one to be the smaller or anything like that. Choose them however you like. And then I'm going to do this limit. Lim n goes to infinity of an over bn. Just plug everything in here. Hopefully, maybe simplify, and hopefully we can actually compute the limit. All right. What do we get? We get, okay, an is 1 over, sorry, I should put my lim out front. I haven't done the lim yet, of course. All right, 1 over n plus 3 divided by 1 over n. And now I'm going to simplify this as much as we can. I don't like this fraction inside a fraction, so I don't know how you like to think about this. When I see such a thing, I decide to write, instead of this division, I write this as multiplication by the reciprocal. So this is really the same as 1 over n plus 3 times n over 1, right? Rather than 1 over n plus 3 divided by that thing, it's the same as multiplied by the reciprocal of that thing. This is how I think through these things. If you think of it in a different way, it's totally fine, as long as you end up with the same point that I do, which is n over n plus 3, right? And then what is the limit of that? Well, this is, I mean, kind of like the one that we just did on the quiz, although easier. I would divide through on the top and the bottom by n, and I get 1 over 1 plus 3 over n. And then when I take this limit, it becomes 1 over 1 plus 0, which is 1, all right? So the limit does exist, and it's not 0. Remember, that's what the test says. If this limit exists and is not 0, then the two convergences are the same. So I'll just say this, the limit exists and is not equal to 0. So the convergence of sum 1 over n plus 3 and sum 1 over n is the same. And we already know the sum 1 over n diverges because it's a p-series with p equal 1. So that means the other one also diverges. So since sum 1 over n diverges, p-series, p equals 1, then the sum 1 over n plus 3 diverges. The end. Right? This is how you do the limit comparison test. It's a little more work, a little more steps to it, but in my opinion, conceptually easier to do and requires less kind of creative inequality nonsense. Any questions about that one? I got some more examples, but this is a simple one. All right, let's do another one. How about just a more complicated looking, similar type of fraction in there. All right. 4 plus n over n to the 4. Now, when you see something like this, you have to decide what am I going to compare this to, right? And this is still some opportunity for creativity. There's no hard and fast rule here. But what I want to do is the book describes this as you look for they call this the dominant terms on the top and on the bottom of the fraction. Like if you imagine that the n is becoming very large, what parts of this are the most important? And the answer on the top is when n is very large, that 4 is kind of irrelevant. If the n is like a billion, adding 4 to it doesn't do a lot. And of course on the bottom, all you have is n to the 4. So that's the dominant terms on the bottom. I'm going to say this looks like, and you just ignore everything else. In this example, it looks like n over n to the 4. All right? The 4 up top doesn't really matter in the large scheme of things. All right? And this, of course, is 1 over n cubed, and that's what I'm going to compare it to. All right, so this is, I'll call this my an. This is going to be my bn. All right, you try to just pick out the parts of the original thing which are the ones that are going to matter when n is super big, and you ignore everything else. All right, let's see. Now you just have to plug everything in and do that limit. So I'm going to do lim n goes to infinity of an over bn. So again, it's going to be a big fraction mess. 4 plus n over n to the 4, and then dividing by 1 over n cubed. And see if we can rearrange, simplify the fraction. I'm going to get, so writing it as a multiplication instead, because that's just how I think about these. It's like that, right? 4 plus n over n to the 4 times n cubed divided by 1. When I multiply these together, the n's will cancel, like the n cubed on top will cancel almost all the n's on the bottom, right? There will be one n left over on the bottom. So this ends up being 4 plus n over n, right? And then we find this limit. This is easy. Again, you divide out the n's. Right? It looks like 4 over n plus 1 over 1. And this, again, is going to be 0 plus 1 over 1, which is 1. All right? So the limit does exist. And it's not 0, which means the comparison is going to be successful. So the limit exists and is non-zero. Non-zero. So the sum 4 plus n over n to the 4 has the same convergence as the sum 1 over n cubed. Remember, those were the two things which we compared. And what about this one, 1 over n cubed? Can anybody say? Converges or diverges? Con or die?
It converges because p is greater than 1.
Yeah, this converges because it is a p series and the p is greater than 1. So you just have to remember those little facts about p series. The other facts about geometric series, that's when the n is in an exponent. Yeah, this converges. Converges because it's a p series and p is, well, p equals 3, right? Which is greater than 1. And so that means the original thing we started with converges. That's the moral of the story. So the sum 4 plus n over n to the 4 converges. The end, right? This is the limit comparison test. Anybody got thoughts about that? All right, I got 2 more examples, and then I want you guys to try some. Sometimes it can be a little weird to decide what the dominant term is, like I said before. So here's a slightly stranger example, mostly the same, but a little weird. 3n plus 7 up top divided by the square root n to the 4 plus 2. All right. Again, we are going to ignore everything except for the dominant terms on the top and on the bottom. Now, on the top we have 3n plus 7. When the n is very large, the plus 7 doesn't really matter. And so I'm going to say, actually, can I make this slightly more interesting? This is going to be great. Let's make it 3n plus 7 root n plus 10. How about that? This is slightly more interesting. When I look at the top, which term there is dominant when the n is very large? The answer is the 3n is the only one that matters, really, when the n is very large. Now, you also see an n, 7 root n, but when the n is super big, the root n is like nothing compared to what the n is, right? The n is much bigger than the root n. So in this case, the dominant terms are just 3n on the top. And then on the bottom, the plus 2 there, so this is a little strange because it's all inside of a square root, but it turns out not to be a big deal. The plus 2 there doesn't really matter. Really, the dominant term is just this, square root of n to the 4, which of course that is n squared when you simplify that business. So really I'm talking about 3n over n squared, which is 3 over n. So that's what I'm going to compare with in this example. All right. Let's see if we can make it happen. So I'm going to compare in this limit here what I started with, which is this big thing, 3n plus 7 root n plus 10 over square root n to the 4 plus 2, and I'm dividing this by 3 over n. That's what I'm comparing it with. And then we do the same thing as before. We simplify as much as we can and take the limit. So simplify, instead of dividing by 3n, it's the same as times n divided by 3. So this is 3n plus 7 root n plus 10 over root n to the 4 plus 2 times n over 3, right? And now, nothing really obviously simplifies here, but I would just, I guess, distribute the n across the top of the first fraction, and then the 3 can just multiply into the denominator. So this on the bottom is now just going to say 3 times the square root n to the 4 plus, it should be plus 2 in there. Plus 2, it's inside the square root. And then on top, distribute the n across. It says 3n squared plus 7, n times root n, that's n to the 1.5 if you like, and then plus 10n. All right. And now we got to do this limit. This limit is a little strange because of the square root sign on the bottom, but it's not such a big deal. We again are going to divide everything through by the largest power of n. Now, the largest power of n in this example, you might be tempted to say it's n to the 4, but this n to the 4 is inside of a square root, so really we want to imagine this as being like an n squared. We also have n squareds on the top, so I'm going to divide everything through by n squared, right? Or you could say I multiply by 1 over n squared. 1 over n squared. What you get in that case is just 3 from the first one. 7 times n to the 1.5 when I multiply by, when I divide out by n squared, it ends up being 7 divided by n to the 0.5, right? I'm dividing by extra stuff. And then 10n dividing by n squared gives me 10 over n, right? And on the bottom, I'm going to have 3 times, maybe I'll just write it this way, 1 over n squared, square root n to the 4 plus 2. But we can continue to simplify here. Actually, we did 1 or 2 examples like this, maybe last week sometime. You can multiply this thing into the square root sign. It's just when it goes inside, this n squared becomes an n to the 4, because when you move something, when you move something out of a square root, you have to take the square root. When you push something into a square root, you would square it. So it's going to be, we're almost done here, 3 plus 7 over n to the 0.5 plus 10 over n over 3 times, okay, the square root, and now it goes inside and becomes a 1 over n to the 4. That gives me a 1 here, and then plus 2 over n to the 4. All right, and now I'm ready to take the limit. You can send the n going to infinity. It means all those things with n's in the denominators will all become 0. And so what's left when I actually do the limit is going to be 3 plus 0 plus 0. Wherever you see n in the denominator becomes a 0. And this, it all works out to 1, right? It's 3 divided by 3 times the square root of 1. 3 over 3, which is 1. All right, maybe you notice a theme here. I'm always getting 1 for the answer of these limits. It turns out if you choose the dominating terms in the correct way, you will always end up with 1, at least for this type of examples. It doesn't always, in some other kinds of examples, you may not get 1. But okay, anyway, my conclusion is the limit exists and is not 0. The limit is not equal 0, so that means that the convergence of these two things are the same. So that means my original thing, the sum, 3, what was it? 3n plus 7 root n plus 10 divided by square root n to the 4 plus 2, was it? Yep. This and my thing I compared it to was much simpler, just 3 over n, right? Sum 3 over n. They have the same convergence. But what about 3 over n? Let's say, and the sum 3 over n, of course that's the same as 3 times the sum 1 over n, and this diverges because this is the p series with p equal 1. And so the original thing also diverges, and that's it. Pretty great. So my original thing diverges. The limit comparison test, it works, it really works. Anybody got questions about that? I had one more example. All of these that we've done have amounted to a p series. Now this is not only useful when you have a p series. Here's one where the comparison is going to be with a geometric series. So this is 3 to the n over 2 to the n plus n. When you see n inside the exponent, you should begin to think about geometric series rather than the p series. But anyway, don't worry about that just yet. You should, again, think about what are the dominant terms here. Up top, it's just 3 to the n. That's all you see on the top. On the bottom, 2 to the n plus n. You just have to think, when n is super big, which of those two numbers is bigger? And the if you know anything about exponents, you know 2 to the n is much, much bigger than just n, right? When you have n inside the exponent, that's way bigger than any individual power of n would be. So 2 to the power n is the dominant term on the bottom. And so this is what I'm going to use to make my comparison with 3 to the n over 2 to the n. All right, let's do it. The same old thing with the limit. Lim n goes to infinity. It's going to be the original thing divided by the new thing. That, if I write it more sensibly, looks like 3 to the n over 2 to the n plus n times 2 to the n over 3 to the n. I multiply the reciprocal. And then we can cancel, those 3 to the n's will cancel, exactly. And what I end up with is 2 to the n over 2 to the n plus n. And now we're going to do a similar trick as before. You know, usually at this point we would divide through by the highest power of n, but in this case there isn't really a power of n. It's this 2 to the power n. I'm going to divide everything by that. So I'm going to, on the top I'm going to go 1 over 2 to the n, and on the bottom I'm also going to go 1 over 2 to the n. All right. I basically want to put things, I want to put the big stuff in denominators, little denominators, so that I can say those little parts go to 0. So this is the same as, it's going to just be 1 on the top, and then on the bottom 1 plus n over 2 to the n. But when I do this limit, that n over 2 to the n will become 0. That's because 2 to the n is far bigger than n in the limit. That fraction becomes 0. If you like, you could use L'Hopital's rule to justify that little step. But anyway, would you mind if I just tell you? N over 2 to the n becomes 0 because 2 to the n is far bigger than n. So that becomes a fraction where the denominator is way bigger than the numerator. All right, anyway, my limit ended up equaling 1. Okay, so the comparison was successful. That means these two series, they have the same type of convergence. So the sum 3 to the n over 2 to the n plus n has the same convergence as the other sum, 3 to the n over 2 to the n. So we got to look at that then, this sum right here. 3 to the n over 2 to the n. Does this converge or diverge? Now, this is not a p series. Remember, the p series is 1 over n to the power p, which that's not that. This actually is more like a geometric series, which looks like the sum a times r to the n minus 1. The geometric series has the n inside the exponent, right? Can we write this in a format that more resembles that one? We can. You want to write it instead as just one thing to a power. So that 3 to the n over 2 to the n is the same as 3/2 to the power n. And now this is a geometric series with r equals, in this case, 3/2, right? R is the base of the thing, which is to the power of n. Anybody remember your geometric series? Does this one converge or not? The geometric series.
This one diverges, correct? Because r has to be less than 1.
That's right. So I hope you remember from your geometric series, it converges when the r is less than 1 in absolute value, and it diverges when the r is greater or equal to 1. So this one diverges since r is greater than 1. And that means my original series diverges, so which is the point of all this. 3 to the n over 2 to the n plus n diverges. That's how we do it, all right? It'll take you a few minutes, but it's mostly mechanical, you know, simplifying things and taking limits of things. All right, I got some for you to try. We got about 20 minutes left, which is a great amount of time for you all to try. I got 2 here. Your job each time is just tell me, does it converge or not? How about the sum 5n minus n to the 4 over n to the 7 plus n to the 5. And another one, n times 2 to the n over 5 to the n plus n. All right, see what you think. Like I did last time, I think I'm gonna put you all in your own room so that I can go around and see how everybody's doing. All right, I will see you. Oh, sorry. Yeah, you'll have to copy these down before you join your room because you won't be able to see it after you join. How's it going, Maddie? She left. Doing all right, Bobby?
Yes, sir, Professor. I'm about halfway through the first problem. I converted it to the limit, and I'm dividing the an over bn right now.
Great. What did you use for the bn?
For my bn, I used 2 to the n over 5 to the n.
Great.
Is that correct?
Yes. So you're doing the second one.
Perfect.
There was a
Awesome.
typo in the first one. Sorry. In that numerator, it has to be a plus. Plus n to the 4 on top.
Okay. All right. Perfect. Yeah, I think
It
I
doesn't
wrote
really
that by
matter, but
accident anyway.
because everything has to be positive.
You're the best, Professor. Thank you. I got
Okay.
it. You're the man.
Doing okay, Julian?
I think I'm doing good.
Okay, great. There was a typo. This right here should be a plus. I wrote minus before, but remember, everything has to be always positive for these. Otherwise, you can't do it at all. It doesn't really matter. I mean, the steps are the same. But.
Okay.
So what did you compare that one with?
1 over n cubed.
Yeah, great. Yeah. All right, I'll come back in a few minutes. Hello, Gabriella. You doing okay?
I think so at the moment.
There was a typo here. This right here used to be a minus. It really has to be plus because everything needs to be positive in order to do this method at all. Yeah. So what did you make the comparison with for the first one?
I tried to do the n to the 4th over n to the 7th.
Yeah, great. Yep, and it worked out
Yeah, I'm not finished.
so far.
though.
Okay, good. I'll come back in a bit. How's
Sorry,
it going?
I forgot to go into the breakout room.
Yeah, that's all
earlier.
right. You were the only one there, so it doesn't really matter. There was a typo here. This I wrote minus before, but it has to be plus. Otherwise, because everything has to stay positive,
Okay.
and you can't do it. But it's really the same steps either way, though.
Okay. So I was just finishing up the first one, so it did equal 1.
Uh huh.
So then it would have the same convergence as n to the 4th over n to the 7th. So then would you you can't make that geometric, right? Or could
I would say no. It's not geometric, but it's that. Right.
Okay. Yes.
And so that's the
greater than 1 would converge.
Yeah, that converges. Yep. Great.
Perfect.
I'll come back in a few minutes.
Okay.
You doing okay, John?
Yeah, so for the dominant terms, I don't know if it's negative n or is it Negative n to the fourth divided by n to the seventh.
Yeah, that's right. Although, so this, that was a typo. This has to be a plus, because remember that
Okay, so
this method
Okay.
only works if it's positive. Yeah. But if it was something like, 7 n to the 4, I would take the 7 also as part of the dominant term.
so then I would do the first term 5n plus n to the fourth divided by n to the seventh plus n to the 5, and then divide that all by 1 over n to the third.
Yeah, right. Yep.
Okay.
All right. I'll come back in a few minutes.
All right, thank you.
John, you doing all right?
Yeah. Actually, I have a question.
Yeah.
So for the first,
one thing, first of all, there was a typo here. Maybe this is related to your question. It should have been a plus there, because this method only works when everything is positive. Were you wondering if you should take the minus sign?
I'm not sure if that factored in, but
Okay.
for the looks like term,
Yeah.
is it 1 over n cubed?
Yeah, that's right.
Okay.
Yep. And then you make that big fraction and try to simplify everything.
Okay. Thank you.
Yeah, great. I'll come back in a few minutes.
All right.
Hello, John. You doing all right?
Yes, I'm doing well, Professor.
Great. There was a typo in the original problem. This right here, I wrote a minus, but it has to be a plus.
Alright.
That's because everything in these problems needs to be positive, or else the whole thing doesn't work.
Yeah, that's what we were going over before during the class when we had to say I think they were both positive for the.
Yeah, right. So what did you use for your comparison with this one?
For the comparison, I used the 5n plus n to the fourth.
So like when you said this one sort of looks like, you said just 5n plus n to the fourth?
Yeah, is that not what we were supposed to go about?
No, I think that, and then you made the big fraction?
Yeah, I did like the super long. I went like super long about this. Like my problem's pretty long.
Okay. What did you get for the limit?
The limit, I was still working on that one. I was like very confused since I didn't have that addition sign. I still had the subtraction sign.
Oh, okay, yeah. So what you, if you just throw away the denominator entirely, then you're not going to get something that works out. So if you, like when you started doing the limit, was it, you have this part, n to the 7 plus n to the 5, and then you divide it by, is this what you did?
Yeah, like
Yeah.
that.
So this actually, if you take the limit of that, you have to go through a bunch of steps to do it, but eventually this limit you would have gotten 0, I believe,
Alright.
which means in order for this to work, the limit has to not be 0, right?
Mm-hmm.
So this, you should not compare it with that. You should look for, on the top and on the bottom separately, say what the dominating terms are. So like on the top here, between these two, the n to the 4 is more dominant.
The big one. And then n to the seventh on the bottom.
Yeah, right. So this is what you should use for the comparison.
Alright, perfect.
And actually, before you do that, you can simplify. What does that simplify to?
Isn't that just n to the third?
Yeah, n to the 3rd on the bottom. So it's
1 over n.
1 over n to the 3rd. Yeah. Yeah, great. I will come back in a few minutes to see how you're doing.
Alright, perfect. Thank you.
Mm-hmm. You're gone. still doing good, Bobby? You left your room, so maybe that means you're done.
I accidentally clicked the leave button. I hit
Oh, okay.
enter, but I'm still working on the problems.
All right, everything's still going okay?
I'm on
though?
the second one right now.
Great. Do you know there's a restaurant in Bridgeport called Bobby B's?
There's a restaurant in Bridgeport called Bobby B's. I'll have to check that. It's like
True.
fish and chips. I might have seen that.
It's roti. It's
like the Indian food, roti?
yeah, but it's some kind of like Jamaican version. I went once. It was good.
Really, I'll have to give that a look. I love
Yeah.
Jamaican food, like jerk chicken. Whenever we go to the Caribbean with my family, we eat jerk chicken like 5 nights while we're there. My mom cooks it. It's so good.
Yeah,
Beans and
yeah,
rice
yeah.
on the side, amazing.
There's tons of little Jamaican places in Bridgeport. But yeah.
I have to check those out. I love Jamaican food.
Yeah.
Thanks for letting me know.
Yeah, it's called Bobby B's Roti.
Bobby B's roti. Yeah, we'll definitely make a visit
Check
there.
it out. All right,
I
I'm
will.
gonna. Still doing all right?
Yeah, I think I got it.
Great. What did you say for the second one? Did you say it converges or diverges?
It converges.
Yeah, because you get like a 2/5 to the n or something. Is that what you? Yeah. Great. All right. I'm gonna close up the rooms pretty soon. I'm just gonna visit everybody else one last time. Still doing okay over here?
Yeah, I think so. I'm just a little confused on like the second one.
Uh huh.
Can you take the n out of the n to the 2 to the n, or can you not?
Yeah. So yeah, you can ignore the n and just use the 2 to the n, which makes it a little easier. Great. The first one worked out for you?
Yeah, I think so.
All right, good. Still doing good in here?
Yeah, so for the second one though, I got to the end where it was the limit as n goes to infinity of 5n over 2n, but wouldn't that not equal 0?
5
Or
to the
not
n
equal
over 2 to the n? That's right.
So it doesn't equal 1, so it's not.
So what did you use to compare with?
So I did the dominant traits where the dominant terms were 2 to the n over 5 to the n.
Yeah. You should...
I multiplied by 5 to the n over 2 to the n and distributed.
This is what you did, right?
Mm-hmm.
You multiply, so the 5 to the n goes up top, n times 2 to the n times 5 to the n, like that. And then on the bottom, you distribute 2 to the n times 5 to the n plus n times 2 to the n, right?
Mm-hmm.
And then to do this limit, I would divide through everything by 2 to the n, 5 to the n.
Okay.
Is that what you did?
Because I multiplied 2 to the n times 5 to the n is 10 to the n.
Okay, sure.
And then I canceled those out, but then I got left with 5 to the n, 2 to the n, because then the n's canceled. I don't know if that's valid, but could you
5 to the n, 2 to the n.
could you cancel the n's and the 10 to the n's? Oh, never mind. I think I added an
Sorry.
extra 5 to the n or something.
Yeah, maybe. I'm gonna if we further divide everything by n. Oh, this is too much. Sorry, I just realized that the class time is over. For some reason I thought we were going to 10:50, but we're not, right? We're supposed to go to 10:45.
No, we're not. Yeah.
All right. I'll start off next time doing these examples. Sorry about that. All right. See you next time.
Yeah.
All right. Class time is over. Sorry, for some reason I thought we were supposed to end at 10:50, but we don't. So maybe we will just go over these at the beginning next time as a little refresher. All right. Have a great weekend, everybody. See you next
Awesome,
time.
Professor. Thank you. Have a great